Hi everyone, this is Hwanjun Song, a research scientist at Naval AI Lab. From this slide, I would like to introduce two more research directions for handling noisy labels, the loss adjustment and sample selection. The loss adjustment is one of the popularly used approach that modifies the loss of training example before updating the model. So it follows the general pipeline below. First, it performs a forward step on a given mini-batch. Next, the computed loss is no longer reliable because of the noise labels. It tries to modify the training loss of all examples. There are two alternative ways, importance reweighting and relabeling. The first one, the importance reweighting, is reweighting the loss by multiplying the sample importance, which is a scalar value denoted by W here. And the importance value can increase the loss of the clean examples while decreasing that of noisy examples to minimize the negative influence from the noisy one. And however, the second one tries to relabel or refurbish the given label y tilde into a more reliable label to modify the training loss as well. Then the model is updated based on the modified training losses for robust update. So I prepared three recent work in this direction. The first one is active bias. Naturally, all the training examples have different importance for training, isn't it? So for example, there are three images labeled as cat here. Two are clean ones and one is noisy one. And the right one is the model's prediction over the training epoch or iteration. So for the cat images, if the model predicts its true label, the annotated label, consistently over the epoch, then this means the example is too easy. That is, it is not that informative for better generalization. However, if the model predicts the long labels, different to the annotated one, frog here, then the example is too hard to learn, or it could be a noisy example. Therefore, the key idea of active bias is to emphasize the uncertain examples where the model's prediction are inconsistent. And to compute the uncertainty of each example, it maintains all the prediction probabilities for the target label and computes their standard deviation as the uncertainty measure. So the value is normalized across all the examples in the current mini batch and then used to reweight the loss of training examples. Like active bias, finding a reweighting rule in heuristic manner, the active bias use the standard deviation could be good for a specific data, but an optimal weighting function is very hard to specify manually because the rule is highly depends on various factors like noise type or noise ratio or the data distribution of a given data. So MetaWeightNet, this work proposed to parameterize the weighting function with a simple linear layer. In terms of the model training, in addition to the target model, the meta model pi here should be trained for the weighting function as well. Therefore, this approach requires a clean validation data for updating the meta model for the clean supervisory signal. So the meta model pi is updated such that it can reduce the loss of the clean validation data, not for the training examples, isn't it? So this model is very model agnostic or data agnostic to find the optimal weighting rule. However, the limitation of this work is the need of clean validation data, which is very hard to acquire in practical scenarios. Different from the two previous work, this is a relabeling approach for loss correction. In the presence of label noise, the annotated labels are not reliable. So this approach proposed to mix the given label y tilde with the model's prediction p, because the model's prediction is able to magnify useful underlying information in training data before the overfitting. So it can adaptively update the label of each example over the training epoch. Look at the example below. A dog example is mislabeled as cat, so its target label is incorrect. So this approach mixes the model's prediction P with its target label Y tilde, thereby generating are more reliable labels. So simply speaking, as shown in the equation below, the mixed label is used as the next target label to fit, where the alpha is the balancing term between the given label and the model's prediction for mixing. This slide shows another research direction for handling noisy labels, which identify clean examples from noise data. Similar to the loss correction, it first performs the forward step for a given noise minibat B and identifies the set of clean examples from the noise minibats. Here, if the examples satisfy a certain condition, it is selected as the clean one, and then the model is updated only using the selected clean set. The main challenge of this direction is which criterion should be used for identifying the clean example from the noise data. The most popularly used criterion for sample selection is the small loss tree. It is very intuitive because the memorization effect of deep neural networks. Deep neural networks, in general, learns clean patterns in the clean data or clean examples. After that, it starts to overfit noise patterns in corrupted example. Because clean pattern is mostly easy to learn compared with the noise examples or outlier. So as you can see, the figure below, there is an interesting connection between the training losses and clean examples. This is the loss distribution of clean and noisy examples. Because the clean examples are easy to learn, they exhibit smaller losses than noisy examples. Therefore, the small loss examples in the left side are selected as clean training examples for robust learning. That's why this is called the small loss tree. There have been a lot of work inspired by the small loss tree. The most representative work using the small loss tree is co-teaching. It adopts the small loss tree as well as the co-training mechanism. So it maintains two networks. So the given mini batch is used for the two networks as shown in the figure below. And then each network identifies the small loss examples from the given mini batch. And then instead of using the selected small loss examples directly, they try to cross the selected set into their peer network. The benefit of crossing their selected set into their peer network is that the selection error occurred in the selection phase will not directly transferred back to itself. A different approach based on the small loss tree is iterative trimmed loss minimization. In this approach, instead of using the two networks, it repeats the training process, training the model multiple rounds with initialization. As the first round, as shown in the figure below, a pre-trained model is ready. It alternates between selecting the small loss examples and retraining the model. And these two steps are repeated multiple training round for the multiple training round. The benefit of this approach is the quality of selected set is further improved as the training round increases. However, the small loss tree has three critical limitations that hinder its practical use. The first one is requirement of strong supervision to quantify how many training examples should be selected as the clean ones. So as you can see, if the red bar, if the dotted line colored in red, the threshold bar moves to the left side, then only a few training examples, the small loss examples, are selected as clean one, isn't it? However, if the threshold bar move to the right side, then even the noise example in the red area could be misclassified as the clean example. So depending on the threshold bar, it can discard too many difficult to learn examples with true labels, although they have much great impact for better generalization. And the last limitation is its inefficient learning pipeline, requiring the co-training or multi-round training, which definitely add heavy computational overhead in large problem. To resolve this issue, last year we proposed to use the memorized example. for sample selection instead of the smaller tree. Then what is the memorized example? An example X is defined as a memorized example if the majority of its listened predictions is equal to its annotated label. So given an image labeled as a dog, we can store the model's listened prediction over the epochs. And if the major class of the prediction history is equal to the given label, the example is regarded as the memorized one because the model is currently predicting its annotated label with high confidence. So with this concept, we can plot how many clean and noisy examples are memorized over training, as shown in figure below. As you can see, at the early stage of training, deep neural networks are prone to memorize clean examples dominantly. So this paper proposed to select the examples memorized at the early stage of training, which is the noisy robust period, as the clean ones, and only using them during the remaining learning process, which is the noise-prone period, as shown in the figure. One step further, this year at KDD, we propose a new approach called MORPH, which can leverage even noise-prone period to build a better safe set. Recall that in the past work, we leveraged the noise robust period to build an initial safe set. However, in this work, we even leveraged the noise-prone period to expand the safe set initially constructed in the phase 1. So as you can see, the red box in the figure right side is incorrectly included in the previous safe set. So we will remove the incorrected one from the safe set, while the blue box is the examples not included in the previous phase. So we further add those kind of examples in the safe set during the noise-prone period. And the phase 1, the constructing initial safe set, and the phase 2, expanding the quality or quantity, improving the quantity and quality of safe set, is automatically transitioned at the best transition point. So that's why it is called self-transitional learning. However, there are two research challenges here. First one is, when is the best transition point to transit the phase 1 into the phase 2? And second challenge is how to expand the initial safe set by adding more clean examples during the noise-prone period. This slide gives the answer for the first question. The question was, when is the best transition point? Intuitively, the best transition point is the moment when the memorization gap between clean example and noisy examples is maximized, as shown in the figure right side. Because at this moment, the network not only accumulates little noise from the noisy examples, but also accumulates sufficient information from the clean ones. The little noise means the quality of pure memorization, while the sufficient information indicates the quantity of pure memorization. That is, the best point is the best trade-off between the quality and the quantity of pure memorization. To measure the quantity and quality of pure memorization, we introduce two metrics below. The memorization precision is the number of memorized clean example over the O memorized example. This is the denominator of MP is O memorized example, so this is the quality of pure memorization. However, the memorization recall, the right side, is defined by the number of memorized clean examples over all clean example in dataset. All clean example in dataset, so the memorization recall indicate the quantity of pure memorization. Therefore, the best transition point is equivalent to the moment that has high memorized precision and recall simultaneously. Next, for the second challenge of how to expand the initial safe set into a better one, we note that the undesired memorization by the noisy example is easily forgotten by the robust update. So the update rule in phase 2 consists of 3 sub-steps. First, we update the model only with the current safe set ST instead of using the entire current mini batch, because mini batch contains noisy examples as well. Then, due to the robust update, there have some memorization changes for training examples. So to reflect those kind of change, we remove the newly forgotten examples because they are mostly noisy one. As I told you, this one is easily forgotten because it is undesired memorization from the noisy example, while adding newly memorized examples to cover more clean examples. So by reflecting the memorized chain, we can update the initial safe set into a better one during the noise-prone period as well. So, and last, these two processes are repeated during the remaining process. Thus, there are three advantages of using our approach compared with the smaller tree. First, it does not require any strong supervision because it progressively increases the number of selected clean examples. Second, it includes even difficult train examples by alternating updating the model and updating the safe set. Third, instead of using the two networks or multi-round learning, it has efficient learning pipeline by simply splitting a single training round into the two learning phases. This is the main experimental result on the two large-scale real-world noise data compared with the other state-of-the-art algorithms. We use two popular real-world noise data called reFurbish and for the 101N dataset. The noise rate of these two data were reported by 20% and 80.4% respectively. In both datasets, the performance of our approach, the MORPH, is very promising. It improved the test error absolutely by up to 10% in reFurbish version 1 and almost 4% in for the 101N data. As I mentioned, the sample selection, like the smaller streak and memorization-based approach, is very good direction to handling the noise level problems. However, it has a natural limitation that noisy examples, the expected noisy examples, are all discarded to pursue the robust update. However, in terms of the representation learning, if we can use the full train data available, then we can make a stronger model. So for this purpose, there are two prominent strategies to support the full exploration of trained data along with the sample selection approach. The first one is applying a hybrid approach of sample selection and the loss correction. Therefore, we can use the relabeled noisy example together with selected clean ones. So as you can see, the figure right, the blue zone are combined with the red zone, relabeled one, and then the combined set are leveraged to update the model by a backpropagation. The second one is using the selected clean examples as the labeled set, and then the remaining noisy ones as the unlabeled set to transform the problem into the semi-supervised learning. SELFIE is a hybrid approach of sample selection and loss correction. To leverage even noisy examples, it introduced the concept of refurbishable examples that can be corrected with high precision. That is, we only relabel when we are certain for the correction. So the modified update rule is leveraged for the for the robust update. First, it corrects the loss of the refurbishable examples by relabeling when we are certain, and then it combines the loss with the loss of the selected clean examples as well. As shown in the equation below, the left component is the loss of the corrected examples by replacing its label into a better one, and the right component is the loss of the selected clean examples. They are combined to update the model. The main challenge of SELFIE is how to construct the clean set C and the refurbishable set R. For the clean set C, the smallest tree is simply adopted for selection, and for the refurbishable sample, the R, it used the model's prediction to find them, similar to the relabeling approach I introduced in the beginning of the part 1. For example, given a dog image described as a cat, it manages a slide window of side Q for the recent epoch. If the predictions are consistent and different to the annotated one, it is regarded as refurbishable because the model is highly certain to another label for the given images, isn't it? So the original label cat is replaced with the most frequently predicted other label the dog in this example. So there are two main advantages of using the SELFIE approach. It utilizes entire training data by combining the corrected noisy examples with the selected clean examples. Also, it achieves low correction error, the labeling error, because it labels only when the example can be corrected with high precision. And the second approach I will introduce is the transforming into the semi-supervised learning for robust training. The problem of noisy label can be transformed into semi-supervised learning as shown in the figure below. After inference the given examples, we applied a sample selection approach. Here, the selected clean examples are regarded as the label set, and the remaining one are regarded as unlabeled set. Next, we can apply any supervised learning approach for the transform data. The most representative work using the semi-supervised learning with noisy labels is divide mix. First, for the data separation, it fits the Gauss two-component Gaussian mixture model to the training losses for all examples. Because the loss distribution of clean and noisy examples are bimodal, as shown in the figure right side. So if the probability of being clean component belonging to the left component here is larger than 0.5, they are assigned into the label set. Otherwise, the remaining one are assigned into the unlabeled set. And then, based on the transform data, the supervised learning method, the mixed method, was applied to train the model. In addition, it adopts the co-training mechanism as well, thereby maintaining two networks similar to the co-teaching approach. And then they cross the separate data from the two individual networks into their peer network as well. Thereby, they can avoid the selection error caused in the selection process transferred back to itself as well. From this slide, I would like to show a demo of how to use Gaussian mixture model for handling noisy labels, because the Gaussian mixture model is a key technique widely used in noisy label community. As the first use case, it can estimate the loss distribution of clean and noisy examples with the ground truth labels. The loss distribution of clean and noise are mostly bimodal, so it is very useful to analyze the data distribution like things. But without knowing the ground truth labels, it is impossible to draw this distribution. So in that case, we can use the Gaussian mixture models for that. And the next use case is estimating the noisy rate of trained data. It's because many of recent approaches requires the noisy rate as a hyperparameter, but it is quite hard to acquire in practice, isn't it? So we can estimate it by using GMMs as well. The noisy rate is estimated simply by subtracting the average probability of belonging to the left component, because it is clean component from 1. Yeah, this is the equation, very simple. And the last use case is sample selection with Gaussian mixture. We know that the clean probability of each training example could be obtained by the Gaussian mixture component, the left component, I mean. So by only selecting the examples whose clean probability is larger than a certain threshold, then we can construct a safe set, and then we can also train the model by only using them for robust learning. Yeah, then let's see more detail in CoREP. Just a second. Yeah, this is the CoREP tutorial. So there are 3 use cases here, 1, 2, 3, as I explained in the slide. So this is the preparation step, download all the necessary code and import the necessary libraries. And this is the data loaders. In this case, in this tutorial, we use the CPAC-10 data set. However, this data, the training example in this data are mostly clean, almost 100% clean. So we need to inject a synthetic noise. So I selected the symmetric noise of noise rate 40%. So the symmetric noise distribute the noise ratio into all class labels with equal probability like this way. And then we need to prepare a pre-trained model for our 3 use cases. And this is the first use case of estimating the loss distribution with GMMs. We have a model pre-trained, isn't it? Then the next one we have to do is accumulate all the training losses like this way, iterate all the example IDs and then accumulate the loss of each examples. But I suggest applying the log function for the training loss, because at the later stage of training, most of the example exhibit zero loss because loss is going down, isn't it? So log function make easy to fit the 2 component of Gaussian mixture, and then create the Gaussian mixture model like here. Have 2 component Gaussian mixture, and then fit this mixture into the training losses. Then we can estimate these 2 loss distribution for clean and noisy example by using this function GMM.predictProba. And what interesting is that this below distribution is the distribution obtained with the ground truth one. However, the estimate one looks very similar with this one. So that means Gaussian mixture is very effective estimate the loss distribution. And for the second use case of estimate the noise ratio, this is very easy to estimate because, as I told you, by subtracting the expected clean probability, the mean of the clean probability for each example. And if we subtract this value from 1, then we can estimate the noise rate. When the noise rate was 40%, this is ground truth noise rate, the estimate one was 46.58%. So the difference is not that large. So very good value to use. And the last use case was the sample selection with Gaussian mixture. So let the threshold be 0.5. Then if the clean probability of each example is larger than the given threshold, then let's accumulate the example into the selected set. And then we can train the selected set by using the general training pipeline. We only need a few lines in the middle, like this way. So as I told you, the selected set is clean examples expected from the Gaussian mixture model. Then we only use the selected safe set for training. So instead of using the entire mini batch, we can check whether the index of the given example is belonging to the this safe set. By doing this, we can train the model for handling noise label. So this is the end of the correct tutorial, and let's go back to our tutorial slide and make the conclusion in part 1. Robust training algorithms are being very actively studied to fight with the noise label inherent in trained dataset. So, and for evaluation, we can use artificial noise, the symmetric or asymmetric noise, by injecting them into the benchmark dataset, or we can simply use the real-world noise benchmark data like the Animal 10N. And we also introduced 4 popular research directions for handling noise labels: robust architecture, loss adjustment, and sample selection, as well as their hybrid approach to support the full exploration of training data. If you are interested in further detail or in this area, then I recommend you to read my survey paper, The Learning from Noise Labels with Deep Neural Network, a survey. Professor Steven will continue this tutorial with the topic Fairness against Data Bias. Thank you.